So let's start. Last time there was some indices didn't match. I mean, it was homework for everybody to find the, where should be correction, right? So we checked. So the statement was like this: so that we had inner product on functions, on smooth functions on compact Lie group, and we had matrix elements of a representation V, and if we consider inner product of such two things, then it's delta ik delta jl over dimension of V. And in the proof, we had the following map from V to V, phi ki for each k and I. And it was like this: rho V of G E k I rho V of G inverse d mu of G. So this is Haar measure. And so this was a map from V to V. So this is just elementary matrix with one on intersection of kth and ith place. And we figured that this is homomorphism of representation, so it's intertwining operator. And so therefore phi ki was cky times identity on V. And so we found that cky, by computing traces of these things, we found that cky is delta ki over dimension of V. Right. On the other hand, we wanted to compute L jth element of this. So L jth element of phi ki. I'm just trying to go to the place where I had minor mistake, so it will be easier for you to write a notes to the lecture, right? So so we have to compute this, right? And this is integral over G rho LK. Well, not exactly this, but something similar. It doesn't really matter for which one we will prove. So rho ji V. So G, and this is like this. So yes, and so anyways, in my notes, just I don't want to repeat all the argument. I just want to point out that we deal with the following expression: rho LKV, rho IJ G inverse. So from here to here is because of unitarity of our representation. And in my notes, I had JI here. So if you try to track through the proof, so I wrote JI last time, but it should be IJ. So this is where mistake was, and then everything should match. Okay, it's something from last time. Now, okay, this one I would like to keep. Right, so I have row ij, row kl is, so I should match k, j should match l in order to be something non-zero, and then it's 1 over dimension of v if they match. Okay, and then now next thing that we would like to introduce is a character of representation v. So by definition, a character of a representation. So I would rather, so since I fixed the representation, I should write the character of a representation. V of, well, I can take for now just some Lie group for Lie group G, but a little bit later we would like it to be compact. But the character I can define for any Lie group. Is the function, so is a function on G defined by, so we denote it by high V of G, so we just take and compute trace of the matrix row V of G, trace over the space V. This does not depend really on any basis that we choose on V. So this is the definition. But if we chose a basis and we have matrix elements corresponding to this basis, right? So then this is of course just this from 1 to dimension of V. Okay, so let us discuss some properties, useful properties of characters. Formulated in form of lemma. So the following holds. Well, character. So I will write a bunch of trivial things, but still they're worth mentioning. So character of just trivial representation is 1. Character of direct sum is sum of characters. Character of tensor product is product of characters. Character is invariant with respect to conjugation. GHG inverse is high V of G. And fifth is that if my group G is compact, I can write high, I have the following: high of V star is high V bar. So I think this only happens for compact G. Because we need unitarity of our representation. So okay, let's see why all this holds. So just looking at definition, right? So which ones are obvious. So this one is obvious, right? So trivial representation is where any gx is 1. Traces of 1 is 1. This is also obvious because trace is, so you have two blocks. So trace of is just sum of traces of these two blocks. So 2 is obvious, and 4 is also obvious because trace is invariant with respect to conjugation, right? So these are obvious from definition. Well, 3 is also not some magic. It's just I mean, some elementary linear algebra, right? So what should I write here? So 3 follows from the following fact. Say it again.
It will be just the trace of tensor product.
Yeah. Right? Yeah. So exactly. Just let me write it down. So what I have is this, right? If I have one linear transformation, right, from V1 to V1, and another linear transformation on some other vector space, then, well, I have L1 tensor L2 on tensor product of V1 and V2. And I just trace, so then trace over tensor product of L1 tensor L2. I just trace over V1 of L1, trace over V2 of L2. Just exercise in linear algebra if you don't know that. Just, I don't know, you can fix a basis and see that two traces just multiplied. All right, and number 5. Number 5. So what should I? So I should write rho corresponding to V star ij. So this is just by definition of the dual representation. So if I think of so this, if I fix some basis, right? So okay, let's start from the beginning. So since G is compact, right? V has invariant form. Which is inner product, right? And let me fix some basis of V. So it's orthonormal basis of V with respect to this form, right? Then, well, I can consider dual basis, right? And consider an element. So I have rho V star of G. So it's a linear transformation from V star to V star, right? And I can consider its ijth element of this matrix of this transformation in basis which is dual to this one, right? So this is in basis v1 star vn star, right? But so if I think of this as, you know, columns, right? So these are row vectors. Then my product is just, you know, usual Hermitian product, right? And then and then just by definition, by definition of how G acts on V star, if I have action on V, this will be just rho. I should take transpose matrix corresponding to V and take G inverse. So remember, we had this. So if I have representation V, have linear functional, how G acts on this linear functional. I precompose with the action of G inverse. So this were inverse. And I precompose means that it acts on F as on rho, right? So therefore I have transposition here. So this is just from our definition, and then we use unitarity to write this as rho ij v of G bar. This is because this is invariant form. This representation is unitary, right? Because U is unitary, not U, V is unitary. And this is basically it, right? So my trace is just sum of diagonal elements, right? So if I replace V by V star, I mean, every element of the matrix just is replaced with a bar. Okay. So therefore, 5 follows. All right. So these characters, they are useful for, in particular, decomposing. So character gives me a correct notion of the size of my representation, in a sense, right? And moreover, it behaves well under tensor products and sums, and so I can take and I can decompose the tensor products of representation into direct sums of irreducibles just using characters. And why I can do it in particular because characters are actually orthonormal with respect to the inner product that we have on functions on G. So again, just to recall that we already have it there, right? That if I have two functions, f and h, or f1, f2, then I compute its inner product as follows. I compute f1 of G, f2 of G bar, d mu of G, right? And so we have the following proposition. Let me fix two irreducible complex representations of G. So let VW be two irreducible complex representations of compact Lie group G. Okay, then we have the following. If I compute inner product, this one of two characters, then I get either 0 or 1, right? And if it's 0, then so v when okay, 0 is when v and w are not isomorphic, and 1 way when they are isomorphic. And this just follows. This just follows from this one from our theorem, right? Recall. So we had this one and also rho. So if I have v and w, they're reducible. Right, and v not isomorphic to w, then rho ijv rho abw is just 0. But if v is isomorphic to w, well, in particular, I can just take v equals to w. Then this happens. So this is just simple consequence of what we proved last time. Let's just accurately write it down. So this 0 follows immediately from part 1 of this theorem, right? This is just again sum rho I v, and this is sum rho jj w. Inner product is of course linear. So therefore, if v is not isomorphic to w, then so rho I inner product with any rho jj is 0. So therefore, we have this. Okay, follows. Okay, so let's officially start the proof. So if v is not isomorphic to w, then high v, high w equals to 0 follows immediately from part 1 of theorem. So this is, let's call this also theorem 1, whatever, of theorem 1. So what if v is isomorphic to w? So if v is isomorphic to w, then of course high v equals to high w. We can just find the basis in w such that rho ij of w is just equals to rho ij of v, right? This
follows from the invariance of trace under the change of basis.
This one?
Yes.
No. You don't even need the characters here. It just by definition, what does it mean for two representations to be isomorphic? You just can find basis there. Like you can restate it like this. You can find the basis in w and the basis in v such that corresponding matrices of the action of G will be just equal. So this happens. So I can just take v equals w and compute what is high V? So this is integral over G sum over ij rho I of G rho jj. So basically, I don't know why even writing like this. Let me not write integral and just write it sum, right, over ij rho I v rho jj v, right? That's what we have. Then I look here and see that I should equal to j, right? So this is sum over I, where I equals to j, of 1 over dimension of v. So this is part 2 of theorem 1. Well, this is, of course, so I goes from 1 to dimension of v, right? So this is just 1. So again, nothing happened really. We proved everything last time, just this theorem. Okay, so we have corollary of this proposition. Again, let V be a complex representation of compact Lie group G. So V be complex representation of compact G. And suppose that we have decomposition of character of V into the following sum. So it's characters of irreducible representations with some coefficients nk, k from 1 to m. And nk, well, let's assume for now that they are positive integers, right, natural numbers, but I mean, we'll prove by the way that they are necessary then, natural numbers. And again, I said it, so let me write it down, that Vk here, so for some irreducible representations Vk, and just to define these numbers more or less, so uniquely, I would also like to require that they are different representations. So Vi is not isomorphic to Vj if I is not equal to j. Then I can make a conclusion that I have the corresponding decomposition of V into reducibles. K from 1 to m and k Vk. So in other words, it's enough to look at character, decompose it into characters of reducibles, then we'll have corresponding decomposition of modules of representations. And proof is easy, just follows immediately from orthogonality of characters. We know that G is compact therefore we have complete reducibility, right? So we can decompose somehow. Let's take V, right? So we have V is direct sum or Mj Wj, right? J from 1 to L for some some natural numbers Mj and some reducible representation Wj. Well, we know how characters behave. We know that this character of V should be decomposed into corresponding sum of characters of representations of W's. So we know that high V is then sum Mj high Wj, J from 1 to L. So our goal is to prove that W's and V's, they are the same, and L is, and so that these sums are the same. So that's what, after rearrangement, of course, of the indices. Okay, so what I would like to do is to compute high V, right, with high Wj. So first I would like to so I can plug in this decomposition on this decomposition inside, right? So if I put this inside, I will have sum nk high vk high wj. That's on one hand. On the other, again, I can write down high v high wj. So this is sum over, I don't know, j prime from 1 to L, m j prime high w j prime high w j. So this is non-zero only if j prime equals to j, right? Well, of course, here I also would like to say that they are all different. So therefore, this is just delta j prime j. So I just can see that it is just mj, of course, right? From orthogonality of characters. So this thing, what we got? We got that this thing high wj is just mj. No, this is just combining this line and this line. So we computed two things in two different, one thing in two different ways. So on the other hand, so this just means that wj should equal to one of vk's. If it doesn't happen, then this is just 0, but this is not 0, right? So therefore, wj equals to vk for some k. And in this case, so this sum is 0 for any other k, right? For any other k. Okay, we can put prime here, right? For some k prime. So for k not equal to k prime, this is 0. For k equal to k prime, this is just n k prime. So therefore, nk prime equals to nj. And then just taking different j's, we see that coefficients up to changing the indices for v, vi is the same as wi, right? And ni is the same as mi, right? So I think we proved everything here. Right, let's talk about characters in SL2 case a little bit. Because everything is very, very explicit there. And it's simple, but still useful to look at. Okay, so let V be a finite dimensional representation of Lie of the Lie algebra SL2C. And we learned that any such, so it's finite dimensional, and we learned that it is then completely reducible, right? Last time, using a compact group. So therefore, it decomposes into irreducibles, but each irreducible has weight decomposition, right? It has basis, right, which is eigenbasis for H. That we learned when we studied irreducible representations of SL2. So therefore, V also has weight representation as a direct sum of reducibles, weight decomposition, I mean. So V has weight decomposition actually, you know what, I would like to define even characters in this case not only for finite dimensional, but maybe for infinite dimensional representation. Right, so let me actually erase the word finite dimensional. So let V be some representation. I just assume that there is weight decomposition. Okay, so assume V has weight decomposition. Namely, what it is? It is decomposes it's a direct sum of subspaces that I denote V mu. Mu runs over Z. So where V mu is a eigenspace of H with eigenvalue corresponding to eigenvalue mu. Okay. Then define the character of V as the following series. So I can take sum, so this will be just series in a variable z, high v, and just so these two things that we introduced for groups, and now I'm defining for algebras, will kind of coincide for finite dimensional presentations. But to distinguish, let me write SL, like a small SL here. So this is series in some additional variable z of the following sort. So I just define it to be like this. Of course, as it is, it can be series in. It is a series which is infinite into both ways, right? Which is not very good, but really what I care about right now is only about Remark modules, which is only infinite one way, right? And I can still multiply them. Anyways, so this is the definition. Now, what's relation to the characters for groups that we introduced earlier? Suppose that V is finite dimensional irreducible of highest weight lambda. Then we know so SL2 as a group is simply connected, right? So therefore, this thing is also a representation of SL2C, right? I can actually write now character of E of corresponding to the group. What is this thing? So I would like to, so just by definition, it's trace over V, right? Rho V of SL of G, right? So this is a representation of, so G is an element in SL2C. And I would like to assume that G is diagonalizable. Okay, so G diagonalizable. Then I can continue. So since it's diagonalizable, it's of, so it's rho V of H, and when I diagonalize, I will have diagonal matrix, but since it's SL, so it will be of the following form, right? Determinant of this should be 1, so this should be Z inverse. Okay, then I would like to, so this H and H inverse, they don't do anything for me, because trace character is invariant with respect to conjugation, right, as we figured. So therefore, this is trace of rho VSL of Z the inverse of the following thing. Okay. Then how to compute this thing? So remember, h was this 1, -1. Right? So this is actually z to the h. Right? Or I can write this as, so it's trace rho SL v z to the h. So what is this thing? It's just a series in matrix H, this one. Right, so this is, I think of so I think of z of h as exp of natural log of z h. So this is number, right, and then this is matrix, and this is just a series in matrix. On the other hand, I can use functoriality of exponential map. So I can write down. So I can write down this as trace of over v of the following metric: z to the power rho of SL small v of h. So this is functoriality of exponent. From here to here?
No, the previous.
The previous, from here to here. It's just, if I consider, so I just claim that just in matrices, this matrix equals to this matrix. So basically, if you have any function and you have diagonal matrix, how do you compute function of this matrix?
Just by function.
Two-ish, yes. Yeah. So this as a matrix is this. So replace this with this. From here to here, just right. So I have rho SL capital, right, of exp, and then some number, and then h. And if functoriality says that it should be exp, so this number, so exp of rho SL small, so I have SL small here, of this number. Right? So this number, it can be so goes through to here, right? And then exponent of ln z is just z, right? So it's z, or I mean, from here to here, it's just explanation of what does that mean, right? Z to the power of matrix. Just easier to write it without any works and stuff. Anyways, but what this thing we know is a matrix. It's diagonal matrix. On diagonal I have lambda, lambda minus 2, lambda minus 4, and so all the way to negative lambda, right? So this is just z to the power lambda, lambda minus 2, right? Or again, I can write this as follows. It's z to the lambda, z to the lambda minus 2, z to the negative lambda right? Right, so now I lost trace somewhere here. So at the end of the day, we got so that this equals to z to the lambda plus z to the lambda minus 2 plus z to the negative lambda. But then this is just sum, right? So these are all weight subspaces of my irreducible representations of highest weight lambda. So this is just, by definition, what was high v SL small of z. And, well, you can, so we chose v to be just finite dimensional irreducible, right? But we can just choose any finite dimensional representation, right? And do the same just by linearity. So by linearity, I will have the same thing, that this equals to this, right? So let me put it this way. Similarly, right? For any finite dimensional representation and diagonalizable and G, which is H, Z inverse, H inverse, we have high SL big V of G is high SL small V of Z. It just follows from, again, from complete reducibility, right? And the effect that character of direct sum is just sum of characters, right? So you just do the same, but with all the summands, and that's it. Okay. So why am I writing this is because you can now just take any representation finite dimensional of SL, small, SL2, and decompose it into characters of Lie algebra SL, characters of irreducible representations. And this will mean, if you decompose, that you actually found decomposition of your representation into irreducibles. So why is that? So suppose that you have high V of Z SL small is sum nk high Vk of Z SL small, right? For some nk from which are natural numbers, and Vk's are irreducible of highest weight k, if you wish. Then since you see, since diagonalizable matrices are dense in the group SL, right? We have the same decomposition for capital SL, right? So I have high V SL big of G now is sum over nk high Vk SL big of G, right? So this is because diagonalize. So because of this star. So because of star and the fact that diagonalizable matrices are dense in SL2C. Okay.
Shouldn't you write character of the algebra somewhere there?
Where?
In that formula?
Here?
Yes.
No. This is an element of group.
Yes.
No. Now I really take character of group. So you see here, character of group equals to character.
Then you have like something weird, no?
Why? No. You see, if my matrix G is diagonalizable, right? For each diagonalizable, these two things are equivalent. But then I say, okay, I can extend this only holds not only for diagonalizable, but for everything, because I just take a limit to all matrices from the dense subset to everything. And since polynomials, so these are just some, continuous functions, like smooth functions on G, right? So they are continuous. So therefore, this still holds for any elements. So this is for any G. Does it make sense?
I just haven't seen the first line.
Yes. So yeah, we started with the algebra, and now we'll talk about. And then, well, I can now take this and consider this as I can now take and restrict it to SU2, right? So we can restrict to SU2, and this will give us high VSU of G equals to sum nk high VK SU of G for any G from SU2. But from the corollary that we proved, it means that actually V is a direct sum of this. So the upshot is that if I have decomposition of characters of Lie algebra, I still can deduce that I have corresponding decomposition of representations. It can be seen more directly, right? Because you can say it the other way, that every every finite dimensional representation, if I compute character from Lie algebra sense, right? It will be Laurent polynomial in Z, which is invariant with respect to change Z to Z inverse, right? Because all reducible representations, they behave like that. And we have complete reducibility. But then these things are then form basis for such Laurent polynomials with such property. And so therefore, from such decomposition, it follows that we have decomposition for representations. But I wanted to relate it somehow to groups. So since we have compact groups, we also have it for the algebra case as well. Okay, so yeah, that's everything that I wanted to say about characters for now. So natural thing where to move now is to at least formulate Peter-Weyl theorem. So let's do this. So it's about so it's about decomposition of L2 on G, right, as a representation, or rather bimodal over G. So again, we work with compactly group. So for each irreducible representation V of G, let me fix an invariant inner product denoted like this on V. So it's actually you can use that by sure lemma. There's only like they differ by scalar multiple actually, but so let me fix this scalar more or less. So let V1 Vn be an orthonormal basis of V, right, of some representation V with respect to this form, and let me consider dual basis V1 star Vn star of V star, right? So of course V star is another representation, and I also can fix invariant inner product there, but I need to fix it consistently with the inner product on V. So that's my point here. So we define an inner product like this on V star, well, in a natural way. So I just would like to say that Vi star, Vj star is just delta ij. I would like this basis to be orthonormal with respect to the form that I'm introducing. And now I can define inner product on the tensor product of V star and V. So define an inner product on V star tensor V as follows. So I just defined it on like pure tensors, kind of, right? So F1 tensor W1, F2 tensor W2. So F1 and F2 are elements of V star, W1, W2 are elements of V. So it's 1 over dimension of V f1, f2 on v star, so this one, this inner product, times w1, w2 on v. All right, so maybe I can even put v star tensor v here. All right, so my next step would be to define linear map I don't know, let's call it M, and this is a map from v star tensor v to smooth functions on G, but I want them to be complex valued. So we define this map as follows: M of f star tensor v is just, well, so this should be function on G, right? So I take this and evaluate it on an element G. So I would like this to be f star of G v. G acts on v. So this is the definition. Let me denote, so let G hat, so it's not an operator like in quantum mechanics. It's just nothing. You can. It's a functional. Yes. So let G hat be the set of isomorphism classes of representations of G. So this inner product, right? Inner product that we introduced on v star tensor v, and map M can be extended to the following direct sum. So it's direct sum, infinite direct sum. And I consider different classes of, okay, I need irreducible representations of G. So I take class here with the representative Vi, and so I sum up over all classes, and then I take Vi star tensor Vy. So these are all finite linear combinations of f from here and v from here, tensor v from here, right? But direct sum is infinite. So we extend. So map M is extended just by linearity, and this thing is extended by saying that direct summands are orthogonal. Different summands are orthogonal. So by saying that different direct summands are orthogonal. So we have the following proposition that is actually follows from all our definitions. The map well, M, right? It's from this direct sum, Vi go over all irreducible representations, non-isomorphic, to C infinity G C is, so it preserves inner product okay, right. Let's see why. So again, it just follows from all the definitions that we made and from the theorems that we had before, but still let's check it accurately. So let me fix some Vi. It's a reducible representation, right? So V, it's some Vi where Vi is a representative of the class in G hat. So again, let me fix orthonormal basis and its dual. So it's orthonormal basis on V and its dual. Then I just would like to compute, so I would like to take Vi star tensor Vj. So it's an element in Vi star tensor Vi. Then I compute the map M. So it gives me a function which I evaluate at G. And what actually happens is that this is exactly ijth element of the matrix corresponding to the action of an element G in basis ij. So it's just again some linear algebra, right? So another way how to write matrix elements is just, it's like that, right? Or I mean, it's just, or you can check it directly. Okay, so this is ijth element. So ijth element of matrix rho V of G in the basis Vi. Okay, but then if I take, so this is my definition, right? So this is my map, really. So you can check. So you can look at here and check that this is true before I erased. So I have this. So I need to compute Vi star tensor Vj inner product with Vk star tensor Vl. right? So our inner product in here. But then I look, all right, I have this, right? But then I would like to, right, so this we compute just using this, but this is orthonormal basis in V star, this is orthonormal basis in V, so it actually gives me 1 over dimension of V, right? And then delta JIK, delta JL. Right? On the other hand, let me take M of this and M of this, and compute its inner product, but as functions on G, right? So, but we figured out that this is just rho Vij, rho V KL. But this, we know what it is. It's the same thing, right? It's just this by theorem 1. So indeed, inner product, this map respects the inner product. So it means that in particular, it means that this map is injective, right? Because it's an inner product, right? If I take an element which was not 0 in here, right? Compute its compute its inner product with itself, right? It will be not 0. But then I compute image of it, and so therefore inner product in here of the image with itself is not 0. So therefore image is not 0. Okay. So corollary of proposition is that M is injective. Is it clear why? Adrian?
No.
Not clear. So you should tell me. So again, let me take. So I have two things, this one and this one. So I would like to see that if I take something not 0 on the left-hand side, then it gives me something non-zero on the right-hand side. So let me take something non-zero, say, I don't know, x, on the left-hand side, right? It's in this direct sum. So this is not 0. In particular, if I compute x with x, so let's again, okay, this is proof of corollary. This is actually positive, strictly positive. But then m of x with m of x also strictly positive, because this equals to this. So therefore, m of x, since it's inner product, m of x cannot be 0, right? So therefore, m of x is not 0. All right. So we have some injective map from here to here. one more computation that I can allow myself to show you during the lecture is that this map is actually preserves, it respects also structure of G module here and here. And by the way, this is right and left G module as well as this one. So it's bimodule. And so M preserves both right and left actions. So let's check this. So I claim that both direct sum and C infinity of GC are G bimodules. So they admit left I should say, even say commuting left and right actions. It's just yeah. So for me, just look at this as a representation of G. So it's
no, group algebra, we understand it as some formal sums, right?
Yeah, still model it's something infinite dimensional. Why not? Yeah, you can if you cannot think of modules other than over rings, yeah, you can think of group algebra. What I mean here is that I have left and right action. So let's see, and they are both, they commute actually. So actions, what about this? So actions on V star tensor, well, direct sum. So left action, so this are very natural. So I take G and it acts as follows. It just F tensor, it just acts on this, on V. And right action, so right action sometimes is denoted by dot G from the right, so it acts from the right. It is, so I take F and precompose it with action of G without any inverses. Then it's right action. No parentheses here, like this. So these are your actions, left and right actions on this thing. So what are actions of G on C infinity GC? Okay, so here it's a little bit funny because left action is given by multiplication from the right, and right action is multiplication from left. Just because it's functions, everything is reversed. Actions, right action of the group on itself becomes left action on functions, right? And this means it's just like precomposed with the right multiplication by G, my function. So in the sense that we discussed in last lecture, right? We define this for any form, in particular zero form, which is just functions. Okay. So proposition so M is homomorphism of G by modules. Let's just check that M respects, say, I don't know, left action. And then right action is just similar. So check, so proof, check that M respects left action. Okay, I take M of G acting on F tensor V and evaluate it at some H. So this is M of F tensor G V evaluated at H. So this is F so evaluated at H, G acts on V. But this is by definition, so I take function f of HV and precompose it with this, right? So I take the argument, which is V here, and act it by G and compute this function. So that's what's here. And this is LG star of M of F tensor V at H. So indeed, left action here corresponds to left action after the action of after the map. Okay, and so now we are ready to formulate the theorem, which is called Peter-Weyl theorem. Which states that the map M can be extended to an isomorphism of bimodules so on the left you have this sum Vi star tensor Vi. Vi is a representative of a class and G hat. But I should write hat also here, which means completion of this with respect to the metric given by the inner product that we introduced in here, right? So this is completion with respect to metric given by this form that we introduced on V star tensor V. And then I map it to L2 of G, L2 with respect to this to Haar measure. and which is also, so it's an isomorphism of bimodals, which is also isomorphism of Hilbert spaces, right? So these are Hilbert spaces with respect to this. So they are complete with respect to this metric that is given on both sides. Is an isomorphism of Hilbert spaces. We are not going to prove it. It's just it takes more time that it's reasonable to spend during lectures. So it will be just big analytic detour to, which is still good thing to do, but we have other things to do. So, anyways, we have. I would like to make a couple remarks about this. First remark. Is that characters play some role in here. So characters, he vi as vi again runs over all irreducible representations of G. So this is actually orthonormal basis in L2 of G with d mu, right? So this, of course, you have some basis in here, right? Given by so if you fix orthonormal basis here, dual to it here, right? Then the map will give you matrix element, right? In the way that we did in the lecture, right? So in particular, there are if you have elements here that give you characters here, and the statement is that characters form an orthonormal basis, like in Hilbert, in Hilbert space sense, right? So it is so linear combinations are dense in L2G d mu, but not in the whole thing. In this, I should, I guess, maybe do it like this: C, G, right? So that means, so these are functions invariant with respect to conjugation. And well, remark 2 is that the statement can be simplified a little bit, but still some work to prove it. So if your G is actually algebraic group, then you can consider like a polynomial functions on G, so coordinate ring. Then you can get rid of, don't consider hat here, and just will be direct sum of vi tensor. vi star. So the simplified version of this, which is still non-trivial, is such an isomorphism. And usually people study like an analogs of this when your G is just discrete group. And so this is very easy statement, and this sum is actually finite. So like in mathematics courses, people first start with representations of finite groups, and then this isomorphism is much more understandable there. Right. Okay. So we conclude the material about integration at this point. Right. So I'm over. So we conclude everything, lecture and material about integration. So next time we will start some structure theory of Lie algebras.
So here we understand similar isomorphism that there are only countable number of representations of yes.
Yeah, it's another story, right? So actually,
because we have a Hilbert, since characters are basis in Hilbert space, that's why we have.
Well, I didn't say anything, so you don't need it actually. So it's just finite, like you can understand. The left-hand side is finite linear combinations of elements from here.
Yes.
And
it's,
and then it's somehow you complete it. You make it complete with respect to inner product that you introduced. How you do this is another story. But another question is, can we say anything about this G hat, right? Is it countable? Is it?
yes.
So the thing is that if G is compact, it's countable. If it's not, then you have some continuous series there. Of representations, I mean, and it's not a like complicated story. If it's finite again, then it is finite.